Before atoms formed, before light could travel freely through space, before the universe had recognizable structure, there was a single second during which everything fundamental took shape. Tonight, we're exploring that first second after the Big Bang, a period when the universe transformed from an inconceivably hot, dense state into something that would eventually allow matter as we know it to exist. This opening second contained epochs that reshaped reality multiple times. Temperature dropped from values we can barely express mathematically to levels where the first stable particles could form. Forces that govern everything today separated from a unified whole. The seeds of all future complexity emerged during this brief window. We'll move through these transformations slowly, examining what physics tells us about conditions so extreme they challenge our everyday understanding of how things work. Get comfortable as we trace the universe's earliest moments, when time itself began, ticking forward and space started its expansion that continues to this day. Welcome to Sleepy Time Universe, where we explore the cosmos at a pace designed for rest and reflection. We move slowly through ideas, allowing each concept time to settle. The universe's first moment, the Planck Epoch, represents the earliest fraction of time we can meaningfully discuss. This period lasted from time 0 to approximately 10 to the negative 43 seconds. That's a decimal point followed by 42 zeros and then a 1. The number is so small, it defies intuitive comprehension. During this infinitesimal interval, the universe existed in a state where our current physical theories cannot provide reliable descriptions. The Planck Epoch takes its name from Max Planck, the physicist whose work on quantum mechanics revealed fundamental limits to how finely we can divide space and time. These limits aren't merely technological, they represent actual features of reality. Below certain scales, our equations produce infinities and contradictions. The fabric of space-time itself becomes subject to quantum uncertainty during the Planck epoch. Temperature during this period exceeded 10 to the 32 Kelvin. To put this in perspective, the core of our Sun burns at roughly 15 million Kelvin. The Planck temperature is a trillion times hotter. At such temperatures, particles acquire energies high enough that their quantum wavelengths become comparable to their gravitational radii. Gravity and quantum mechanics, usually operating at vastly different scales, become equally important. This creates a regime where neither general relativity nor quantum field theory alone can describe what happens. Density reached approximately 10 to the 93 grams per cubic centimeter. If we somehow compressed Mount Everest into a space smaller than an atomic nucleus, we would approach but not reach Planck density. Matter and energy existed in such concentrated form that the distinction between the two ceased to have meaning in the way we normally understand it. The four fundamental forces, gravity, electromagnetism, the strong nuclear force, and the weak nuclear force, likely existed as a single, unified force during the Planck epoch. Just as ice and liquid water are both H2O molecules arranged differently, these forces may represent different manifestations of one underlying interaction. However, we currently lack a complete theory describing how this unification works. String theory, loop quantum gravity, and other approaches attempt to bridge this gap, but experimental verification remains beyond our reach. Space itself behaves strangely during the Planck epoch. Below the Planck length, roughly 10 to the negative 35 meters, smooth space-time geometry gives way to quantum foam. At these scales, space and time fluctuate wildly. Tiny wormholes and disconnected regions might constantly form and dissolve. The very notions of before and after become ambiguous. Causality itself, which requires well-defined temporal ordering, operates differently than in the familiar universe. Energy fluctuations during the Planck epoch occurred with such magnitude that virtual particle pairs, normally ephemeral quantum phenomena, carried enough energy to significantly warp spacetime around them. The universe at this scale resembled nothing in our experience. No comparison captures its nature adequately. We should note what we mean by time zero. In classical physics, zero represents an absolute beginning. In quantum gravity, time zero might instead mark a transition point. Some models suggest the universe could have existed in another form before the hot Big Bang state, with the apparent beginning representing a bounce or phase transition rather than creation from nothing. Other models propose that time itself only becomes meaningful after the Planck scale, making questions about before the Big Bang potentially meaningless, not because we lack information, but because before requires time to already exist. The Planck epoch's brevity shouldn't diminish its significance. During this infinitesimal moment, the universe established initial conditions that would determine its entire subsequent evolution. Every star, galaxy, and atom traces its ultimate origin to whatever occurred during these first 10 to the negative 43 seconds. Understanding this epoch remains one of physics' great challenges. As the universe aged beyond the Planck time, temperature and density dropped enough that gravity began operating distinctly from other forces. This separation marked the end of the Planck epoch and the beginning of an era where our physical theories become somewhat more reliable, though still stretched to their limits. Following the Planck epoch, the universe entered a phase called the Grand Unification epoch, lasting from 10 to the negative 43 seconds to roughly 10 to the negative 36 seconds after the Big Bang. During this period, gravity had separated from the other forces, but electromagnetism, the strong nuclear force, and the weak nuclear force remained unified as a single interaction. Temperature during the Grand Unification epoch ranged from 10 to the 32 Kelvin down to approximately 10 to the 28 Kelvin. While this represents a tremendous cooling from Planck temperatures, conditions remained far more extreme than anything we can recreate or directly observe. The universe cooled not because it radiated heat into surrounding space. There was no surrounding space, but because space itself expanded, diluting the energy density. Grand Unified Theories, or GUTs, describe how the electromagnetic, strong, and weak forces behave as a single force at these energies. Just as electromagnetic and weak forces unify at energies around 100 giga-electron-volts, accessible in particle accelerators, these three forces unify at much higher energies, around 10 to the 16 giga-electron-volts. The universe during the Grand Unification epoch possessed enough thermal energy that particles naturally reached these unification energies. Matter during this epoch existed as a soup of elementary particles and their antiparticles, along with force-carrying bosons, quarks and antiquarks, leptons and antileptons, photons, gluons, and W and Z bosons all mixed together in thermal equilibrium. Particles constantly created and annihilated, transforming between different types. A quark could scatter off a photon and become a lepton. An electron and positron could annihilate into pure energy, which would immediately materialize as a different particle-antiparticle pair. The unified force operated through exchange particles called X and Y bosons. These particles carried enormous mass, roughly 10 to the 15 times the proton mass, making them highly unstable. They could exist only at the extreme temperatures of the Grand Unification epoch. When these bosons decayed, they treated matter and antimatter asymmetrically. This asymmetry would prove crucial. One of the universe's deepest mysteries is why matter exists at all. For every particle, quantum field theory predicts a corresponding antiparticle with opposite charge. When matter and antimatter meet, they annihilate into pure energy. If the Big Bang created equal amounts of matter and antimatter, everything should have annihilated shortly after the universe cooled enough for particles to become stable. We, along with stars, planets, and galaxies, shouldn't exist. The decay of X and Y bosons during the grand unification epoch may explain this asymmetry. These massive particles decayed into both quarks and antiquarks, but not at exactly equal rates. For every billion antiquarks produced, perhaps 1,000,000,001 quarks formed. This tiny imbalance meant that after all the matter-antimatter annihilation occurred, a small residue of matter remained. That residue constitutes everything we observe in the universe today. The physics behind this asymmetry requires three conditions, first outlined by physicist Andrei Sakharov. First, processes must exist that violate baryon number, the count of matter particles. X and Y boson decay satisfy this requirement. Second, these processes must violate certain symmetries relating particles to antiparticles. Third, the universe must be out of thermal equilibrium, meaning reactions don't have time to erase any asymmetries that form. The expanding, cooling universe of the grand unification epoch met all three conditions. Evidence supporting this picture remains indirect. We observe the matter dominance in the present universe, ourselves included, but cannot directly verify the mechanisms that produced it. Particle accelerators can create conditions similar to those fractions of a second after the Big Bang, but reaching grand unification energies lies far beyond current technology. The Large Hadron Collider, our most powerful accelerator, achieves energies around 10 to the 4 giga-electron volts. Grand unification occurs at 10 to the 16 giga-electron volts, a trillion times higher. Some predictions of grand unified theories can be tested. Many GUT models predict that protons should be unstable, decaying extremely slowly into lighter particles. Experiments have monitored large tanks of water for decades, watching for signs of proton decay. So far, none have been observed, which places limits on various GUT models, but doesn't rule out the general concept. Another prediction involves magnetic monopoles, particles that carry a single magnetic pole, either north or south. In our everyday experience, magnets always have both poles. Cut a bar magnet in half, and you get two smaller magnets, each with north and south poles. Grand unified theories predict that very massive magnetic monopoles should have formed during the grand unification epoch. However, we've never detected such particles. This absence creates a problem called the monopole problem, which we'll return to when discussing inflation. Toward the end of the grand unification epoch, as temperature dropped below 10 to the 28 Kelvin, the unified force began to separate. The strong nuclear force, which binds quarks together to form protons and neutrons, split off from the electroweak force, which combines electromagnetism and the weak nuclear interaction. This phase transition resembled water freezing into ice, though the analogy captures only a faint echo of what occurred. During phase transitions, energy gets released or absorbed as the system reorganizes. When the strong force separated, enormous amounts of energy transferred into the fabric of space-time itself. This energy release may have driven a brief but extraordinarily rapid expansion called inflation, which we'll examine in detail next. The universe at the end of the grand unification epoch stood poised for one of the most dramatic transformations in cosmic history. Around 10 to the negative 36 seconds after the Big Bang, the universe may have undergone a period of exponential expansion called cosmic inflation. During an incredibly brief interval, lasting perhaps until 10 to the negative 32 seconds, space expanded faster than light, stretching the universe by a factor that might have exceeded 10 to the 26. In less time than it takes light to cross an atomic nucleus today, the universe grew from subatomic dimensions to perhaps the size of a grapefruit or larger. Inflation theory emerged to solve several puzzles about the universe's large-scale structure. The first puzzle involves the universe's uniformity. When we observe the cosmic microwave background radiation, light from when the universe was 380,000 years old, we see that temperature varies by less than 1 part in 100,000 across the entire sky. Regions separated by vast distances possess nearly identical properties. This uniformity seems strange because, without inflation, these regions would never have been close enough to interact and equilibrate to the same temperature. Consider 2 points in opposite directions in the sky. Light from these regions has traveled 13 billion years to reach us, and the regions currently lie about 46 billion light-years apart due to the expansion of space. In the early universe, before inflation, these regions would have been too far apart to have ever exchanged light or any other signal. How then did they end up at almost exactly the same temperature? Inflation solves this by proposing that these apparently distant regions were actually in close contact before inflation occurred. They equilibrated to a common temperature when the universe was incredibly tiny. Then inflation stretched them apart faster than light could travel between them, preserving their similar properties. After inflation ended, they remained too far apart to affect each other, but they started with matching conditions. The second puzzle involves flatness. The geometry of space can be curved, like the surface of a sphere or a saddle, or flat like an infinite sheet of paper. Our universe appears flat to high precision. Measurements of the cosmic microwave background indicate that if space has any curvature, it's extraordinarily slight. However, flatness is unstable. Even tiny deviations from perfect flatness in the early universe should grow rapidly as space expands. For the universe to be as flat as we observe today, it would need to have been flat to within 1 part in 10 to the 60th in the first second. This fine-tuning seems implausible without some mechanism to enforce it. Inflation solves this through rapid expansion. Imagine drawing a small circle on an uninflated balloon. The surface curves noticeably around the circle. Now inflate the balloon to enormous size. The curvature within the original circle becomes so gradual it's effectively flat. Similarly, inflation stretches space so dramatically that any initial curvature becomes negligible. Whatever region we can observe today represents just a tiny patch of a much larger universe, and that patch appears flat regardless of what the overall curvature might be. The third puzzle involves magnetic monopoles. As mentioned earlier, grand unified theories predict that magnetic monopoles should form during phase transitions in the early universe. If these monopoles formed before inflation, their density would have been diluted to practically nothing by the exponential expansion. This explains why we don't observe them despite their predicted existence. The mechanism driving inflation involves quantum fields. In particle physics, every particle corresponds to a field permeating space. Electrons represent ripples in the electron field, photons represent ripples in the electromagnetic field, and so on. During inflation, a hypothetical field called the inflaton dominated the universe's energy content. This field existed in what's called a false vacuum state, a configuration with high energy but temporary stability. A useful analogy involves a ball resting in a slight depression on a hillside. The ball is stable momentarily, but not in the lowest possible energy state. Given a small push, it will roll down to the valley below. The inflaton field during inflation resembled this ball. It occupied a high energy state that was stable for a brief time, but eventually rolled to a lower energy configuration. While the inflaton field remained in the false vacuum, it exerted negative pressure. Negative pressure is counterintuitive. Positive pressure pushes outward, like air in a balloon. Negative pressure pulls inward, like tension in a stretched rubber band. However, Einstein's equations describing gravity show that negative pressure causes space itself to expand exponentially. The inflaton field's negative pressure drove the rapid expansion of inflation. This expansion differed fundamentally from ordinary cosmic expansion. Normal expansion occurs because space stretches over time, but the expansion rate typically slows as the universe ages and matter density decreases. During inflation, the expansion rate remained roughly constant even as space grew. This created exponential growth, where each tiny interval of time doubled the universe's size. Over mere fractions of a second, repeated doublings increase size factors to staggering values. Consider that 60 doublings increase size by a factor exceeding 10 to the 18. During inflation, hundreds or thousands of doublings may have occurred, depending on the specific model. This transformed a region smaller than an atom into something potentially larger than the visible universe today. The numbers become so large that their exact values cease to matter much. Inflation made the universe incomprehensibly larger regardless of precise details. Eventually, the inflaton field rolled to the bottom of its energy hill, reaching what's called the true vacuum. When this happened, the false vacuum energy converted into ordinary matter and radiation. This conversion process, called reheating, filled the universe with an incredibly hot, dense plasma of particles. Inflation ended, but it left the universe in the hot, expanding state described by the standard Big Bang model. Reheating restored high temperatures after inflation had cooled the universe. As the inflaton field oscillated around the minimum of its potential energy, these oscillations decayed into particles. The energy that had been stored in the field became the kinetic energy of matter and radiation. Temperature shot back up to levels possibly as high as 10 to the 27 Kelvin or more. From this point forward, the universe evolved through continuous expansion and cooling without further dramatic phase transitions. Quantum fluctuations during inflation left permanent imprints on the universe. At quantum scales, fields fluctuate randomly even in empty space. During inflation, these tiny fluctuations were stretched to cosmic scales by the exponential expansion. Regions where the inflaton field had slightly higher energy expanded slightly differently than regions where it had slightly lower energy. These differences created tiny variations in density, about 1 part in 100,000, that would eventually grow through gravitational collapse to form galaxies, stars, and planets. We observe these primordial fluctuations in the cosmic microwave background. The tiny temperature variations we measure across the sky trace back to quantum fluctuations during inflation. This represents a remarkable connection between the smallest and largest scales in physics. Quantum effects during the first fraction of a second determined where galaxies would form billions of years later. Inflation also generates gravitational waves, ripples in space-time itself. Just as electromagnetic waves carry energy through oscillating electric and magnetic fields, Gravitational waves carry energy through oscillating space-time curvature. The rapid expansion during inflation should have produced a background of gravitational waves with specific properties. Detecting this primordial gravitational wave background would provide strong evidence for inflation and reveal information about the energy scale at which inflation occurred. Several experiments search for these gravitational waves by looking for their effects on the polarization of the cosmic microwave background. Gravitational waves passing through space create subtle patterns in how the ancient light is polarized. In 2014, the BICEP-2 experiment announced detection of these patterns, generating excitement that inflation had been confirmed. However, further analysis revealed that the signal came from dust in our galaxy, rather than primordial gravitational waves. The search continues with increasingly sensitive instruments. Inflation remains a theory rather than established fact. While it elegantly solves several cosmological puzzles and makes testable predictions, direct confirmation proves challenging. Alternative theories attempt to explain the universe's flatness and uniformity without invoking inflation. Some propose that the Big Bang was actually a bounce from a contracting pre-existing universe. Others suggest modifications to general relativity that affect the universe's earliest moments. Most cosmologists favor inflation because it naturally explains multiple observations simultaneously and makes concrete predictions. The theory has passed several tests. The specific pattern of fluctuations in the cosmic microwave background matches inflation's predictions. The universe's flatness and large-scale uniformity align with inflated scenarios. Still, we await definitive proof through gravitational wave detection or other means. If inflation occurred, it represents one of the most violent and consequential events in cosmic history. In an almost immeasurably brief instant, a process driven by quantum fields transformed a microscopic region into something approaching the scale of the observable universe. Everything we see today, galaxies, stars, planets, arose from that incredibly tiny patch of space, stretched and amplified by inflation's exponential expansion. The universe after inflation continued evolving, but at a pace gentle by comparison. After inflation ended and the universe reheated, it entered the Electroweak epoch, lasting roughly from 10 to the negative 36 seconds to 10 to the negative 12 seconds. During this period, electromagnetism and the weak nuclear force remained unified as a single electroweak interaction. Temperature ranged from perhaps 10 to the 27 Kelvin down to about 10 to the 15 Kelvin. While still unimaginably hot, these conditions fall within the range explored by modern particle accelerators, giving us some confidence in our theoretical descriptions. The electroweak force governs certain particle interactions at high energies. At the temperatures present during this epoch, particles moved so rapidly that the distinction between electromagnetic and weak interactions disappeared. Both arose as different manifestations of the same underlying symmetry. Only 4 types of particles mediate the electroweak force: the photon, which carries electromagnetic interactions, and 3 massive bosons called W+, U-, and Z, which carry weak interactions. During the electroweak epoch, these 4 bosons had equal status. None were lighter or heavier than the others. Symmetry principles dictated that all 4 should be massless, allowing them to travel at light speed like photons do today. The universe at these temperatures respected this symmetry fully. Particles converted freely between different types. Reactions proceeded in both directions with equal ease, and the laws governing interactions displayed elegant mathematical properties. Matter during this time consisted primarily of quarks and leptons. Quarks come in 6 varieties or flavors: up, down, charm, strange, top and bottom. Leptons include electrons, muons, and tau particles, along with 3 types of neutrinos associated with each. During the Electroweak epoch, all these particles existed as a hot plasma, continuously created and destroyed through collisions and decays. Temperature remained too high for quarks to bind together into protons and neutrons. The strong nuclear force tried to confine quarks, but thermal energy overwhelmed the attraction. Quarks moved freely, interacting with each other and with gluons, the particles that carry the strong force. This state, called a quark-gluon plasma, resembled an atomic nucleus melted into its constituent parts. Leptons likewise moved independently, absorbing and emitting the bosons that carry the electroweak force. An electron might emit a W boson and transform into a neutrino. A neutrino might absorb a Z boson and scatter off a quark. These processes occurred constantly throughout the plasma, maintaining thermal equilibrium. The universe's expansion continued throughout the Electroweak epoch, gradually lowering temperature and density. As conditions cooled, the Electroweak symmetry became increasingly unstable. The universe approached another phase transition, one that would separate electromagnetism from the weak force and give mass to fundamental particles. This phase transition involves the Higgs field, perhaps the most celebrated discovery in recent particle physics. The Higgs field permeates all of space, much like the electromagnetic field or gravitational field. However, unlike those fields, which take zero value in empty space, the Higgs field maintains a constant non-zero value everywhere. This non-zero value is what broke the Electroweak symmetry. Before the transition, at high temperatures during the early Electroweak epoch, thermal energy prevented the Higgs field from settling into its non-zero state. The field fluctuated around zero value, and the Electroweak symmetry remained intact. As the universe cooled, a critical temperature was reached, around 10 to the 15 Kelvin or 100 GeV in energy terms. Below this temperature, the Higgs field could no longer be kept at zero value. It underwent a transition to a non-zero state, much like how a magnet suddenly develops north and south poles as it cools below a critical temperature. When the Higgs field developed this non-zero value, it broke the symmetry between photons and W and Z bosons. Photons, which don't interact with the Higgs field, remained massless and continued traveling at light speed. W and Z bosons, which do interact with the Higgs field, acquired mass. This mass made them short-range compared to photons, which is why the weak force operates only at subatomic distances, while electromagnetism extends indefinitely. Quarks and leptons also acquired mass through interaction with the Higgs field. The strength of each particle's interaction determines its mass. Particles that interact strongly with the Higgs field became heavy, while those with weak interactions remained light. This explains why the top quark is massive while the electron is relatively light, and why neutrinos have tiny masses. Each particle's mass reflects how much it feels the omnipresent Higgs field. The Higgs mechanism represents a profound concept. Mass isn't an inherent property that particles simply possess. Rather, mass arises from particles' interactions with a field that fills all space. Without the Higgs field's non-zero value, fundamental particles would be massless and the universe would be dramatically different. Atoms couldn't form, chemistry wouldn't work, and structure as we know it couldn't exist. Discovery of the Higgs boson in 2012 at the Large Hadron Collider confirmed this picture. The Higgs boson represents a ripple or excitation in the Higgs field, analogous to how photons represent ripples in the electromagnetic field. Creating this particle required colliding protons at energies high enough to disturb the Higgs field significantly. The detection of a particle with properties matching theoretical predictions validated decades of theoretical work and confirmed that our understanding of the Electroweak epoch is essentially correct. The phase transition that broke Electroweak, Symmetry, may have produced interesting cosmological effects. If the transition occurred as a first-order phase transition, where bubbles of the new phase nucleated and expanded through the old phase, it could have generated gravitational waves. These waves would differ from those potentially produced during inflation, carrying different frequencies and patterns. Future gravitational wave detectors might observe them, providing another window into the first second. Some extensions to the Standard Model suggest that the Electroweak phase transition could have contributed to the matter-antimatter asymmetry discussed earlier. In the Standard Model alone, the asymmetry produced isn't quite large enough to explain observations. Additional physics beyond the Standard Model might enhance this asymmetry during the Electroweak phase transition. Several experiments search for subtle effects that might hint at such new physics. As the Electroweak epoch ended, the universe had acquired familiar properties. The four fundamental forces now operated distinctly. Particles had the masses we measure today. The stage was set for quarks to bind into protons and neutrons, which would occur in the next phase of evolution. Everything established during the first 10 to the negative 12 seconds, the matter-antimatter asymmetry, the seeds of structure from inflation, the particle masses from the Higgs field, would determine how matter organized itself in subsequent eras. Following the Electroweak phase transition, the universe entered the quark epoch, lasting from about 10 to the negative 12 seconds to roughly 10 to the negative 6 seconds, 1 microsecond, after the Big Bang. Temperature during this period dropped from approximately 10 to the 15 Kelvin to about 10 to the 13 Kelvin. The universe still consisted of a quark-gluon plasma, but conditions were gradually approaching the threshold where quarks would bind together permanently. Quarks interact through the strong nuclear force mediated by particles called gluons. This force exhibits a peculiar property called asymptotic freedom. At very short distances or high energies, quarks barely attract each other. They move almost independently, making the quark-gluon plasma during the quark epoch similar to a weakly interacting gas. However, as quarks separate or as energy decreases, the strong force grows stronger. When quarks try to move apart by more than roughly 10 to the negative 15 meters, about the size of a proton, the force between them becomes so powerful that they cannot escape each other. This behavior contrasts sharply with other forces. Gravity and electromagnetism weaken with distance. The strong force behaves oppositely at scales larger than a proton, growing stronger as quarks separate. If you tried to pull two quarks apart, the energy required would increase until eventually, at sufficient separation, there's enough energy in the field between them to create new quark-antiquark pairs from the vacuum. These new pairs bind with the original quarks, preventing isolation. This phenomenon, called confinement, means that free quarks cannot exist in isolation at ordinary temperatures. During the quark epoch, temperature remained high enough that thermal energy overcame the strong forces confining nature. Quarks existed freely throughout space, forming a hot plasma. Gluons also moved independently, constantly emitted and absorbed by quarks. The plasma remained in thermal equilibrium. with creation and annihilation processes balancing each other. 3 generations of quarks existed in this plasma. The lightest generation contains up and down quarks, which would eventually form protons and neutrons. The second generation includes charm and strange quarks, both heavier than up and down. The third generation contains top and bottom quarks, the heaviest varieties. At the high temperatures of the early quark epoch, all 6 types existed in significant numbers. As temperature dropped, heavier quarks decayed into lighter ones, until only up and down quarks remained in abundance. Antiquarks also populated the plasma. For every up quark, an up antiquark existed nearby. The same held for all quark types. However, thanks to the matter-antimatter asymmetry generated earlier during the grand unification and electroweak epochs, a tiny excess of quarks over antiquarks existed. Roughly 1 extra quark per billion, quark-antiquark pairs. As the universe expanded and cooled, it approached a critical temperature around 10 to the 13 Kelvin, corresponding to an energy of about 150 mega-electron volts. Below this temperature, thermal energy could no longer overcome the strong forces confining nature. Quarks would bind together permanently, forming composite particles called hadrons. Protons and neutrons are hadrons, each containing 3 quarks bound tightly together. The phase transition from quark-gluon plasma to hadronic matter represents another major reorganization of cosmic structure. This transition differs from earlier ones. While the electroweak phase transition involves symmetry breaking through the Higgs field, the quark-hadron transition resulted from the strong forces increasing strength as temperature dropped. The physics describing this transition, called quantum chromodynamics or QCD, has been tested extensively at particle colliders and matches observations well. We can recreate conditions similar to the late quark epoch in modern experiments. The relativistic heavy ion collider in New York and the Large Hadron Collider in Switzerland both produce quark-gluon plasma by colliding heavy atomic nuclei at enormous speeds. When lead or gold nuclei collide, they briefly melt into their constituent quarks and gluons, creating a tiny droplet of primordial matter. This droplet exists for less than 10 to the negative 23 seconds before cooling and hadronizing. But during its brief existence, it exhibits properties matching theoretical predictions. These experiments reveal that quark-gluon plasma behaves as a nearly perfect fluid. Despite being so hot and energetic, the plasma flows with minimal internal friction, much like liquid helium cooled near absolute zero. This unexpected behavior has required refinements to theoretical models, but also provides confidence that we understand the quark epoch reasonably well. Toward the end of the quark epoch, as temperature approached the hadronization threshold, fluctuations in quark density became important. Regions with slightly higher quark concentration would preferentially form hadrons first. These density fluctuations ultimately trace back to quantum fluctuations during inflation, influenced how matter distributed itself once hadrons formed. The connection between quantum fluctuations in the first fraction of a second and the eventual formation of galaxies represents one of cosmology's most remarkable insights. When temperature dropped below about 150 mega-electron volts, quarks began binding into hadrons. This process didn't occur instantaneously throughout the universe. Instead, hadronization happened gradually, with different regions transitioning at slightly different times depending on local density and temperature. The quark-gluon plasma essentially froze into hadronic matter, much like how liquid water freezes into ice. Though the physics involved differs substantially, Most quark-antiquark pairs annihilated as they combined, converting mass into energy. An up-quark meeting an up-antiquark would annihilate into photons. A strange quark meeting an anti-strange quark would annihilate into lighter particles. This annihilation released enormous amounts of energy, temporarily reheating the universe slightly, even as the overall expansion continued cooling it. The slight excess of quarks over antiquarks meant that after all annihilation finished, a residue of matter remained. For every billion quark-antiquark pairs that annihilated, one lone quark survived. These surviving quarks would form all the protons and neutrons in the universe. Every atom in your body, every atom in Earth, every atom in every star and galaxy traces back to that tiny excess of quarks that survived the annihilation at the end of the quark epoch. 3 quarks bound together form baryons, the family of particles including protons and neutrons. A quark and antiquark bound together form mesons, particles like pions and kaons that mediate some nuclear interactions. As hadronization proceeded, the universe filled with various combinations of quarks forming different hadrons. Most of these were unstable, decaying rapidly into lighter particles. Only the lightest baryons, protons and neutrons plus some mesons survived long enough to play roles in subsequent evolution. By approximately 1 microsecond after the Big Bang, the quark epoch ended. Quarks had become permanently confined within hadrons. The quark-gluon plasma phase of cosmic history finished, never to return except in brief flashes within particle colliders, or perhaps in the cores of neutron stars. The universe now consisted primarily of protons, neutrons, electrons, neutrinos, and photons, all in a hot plasma state. The next phase would see these particles interact to form the first atomic nuclei. With quarks now confined within hadrons, the universe entered the Hadron epoch, lasting from roughly 1 microsecond to 1 second after the Big Bang. Temperature during this period ranged from about 10 to the 13 Kelvin down to approximately 10 to the 10 Kelvin, 10 billion Kelvin. While still extraordinarily hot, these temperatures fall within the range that governs nuclear physics processes we can study experimentally. At the beginning of the Hadron epoch, the universe contained protons, neutrons, and various unstable hadrons in thermal equilibrium with leptons and photons. Collisions between particles occurred constantly. A proton might collide with a neutron and produce pions. Pions might decay into muons and neutrinos. Muons might decay into electrons and more neutrinos. All these processes proceeded at rates fast enough to maintain equilibrium. Protons and neutrons during this time were interconverted through weak interactions. A neutron could absorb a positron and emit a neutrino, transforming into a proton. A proton could capture an electron and emit a neutrino, becoming a neutron. These reactions kept the neutron-to-proton ratio in balance with the thermal environment. At temperatures above about 10 to the 11 Kelvin, roughly equal numbers of protons and neutrons existed. The weak force, despite its name, plays crucial roles during the Hadron epoch. Weak interactions allow particles to change types, turning neutrons into protons and vice versa. These transformations require the exchange of W bosons, which we discussed during the Electroweak epoch. At high temperatures, thermal energy easily creates W bosons, allowing frequent weak interactions. As temperature drops, W boson production becomes rarer, and weak interactions slow down. Around 100 milliseconds after the Big Bang, temperature dropped to about 10 to the 11 Kelvin. At this point, thermal energy became insufficient to create W bosons easily. weak interactions. Converting neutrons to protons and back became much slower. The neutron-to-proton ratio began freezing out, ceasing to track the thermal equilibrium value. This freeze-out occurred when the neutron-to-proton ratio stood at roughly 1 neutron for every 6 protons. Neutrons are slightly heavier than protons. A free neutron's mass exceeds a free proton's mass by about 1 part in 1,000. This small difference means that at a given temperature, producing a neutron requires slightly more energy than producing a proton. When weak interactions were rapid, this energy difference didn't matter. Particles constantly converted, and any energy deficit was made up through collisions. Once weak interaction slowed, the energy difference became significant. The equilibrium favored protons over neutrons, leading to the 1:6 ratio at freeze-out. After freeze-out, isolated neutrons began decaying. A free neutron transforms into a proton, electron, and antineutrino with a half-life of about 10 minutes. In the expanding, cooling universe, neutrons decayed steadily. By the time conditions became right for forming atomic nuclei, several minutes after the Big Bang, the neutron-to-proton ratio had dropped further, to roughly 1 neutron for every 7 protons. Neutrinos deserve special attention during the Hadron epoch. These particles interact only through the weak force, making them extraordinarily elusive. A neutrino can pass through light years of solid matter without being absorbed. During the Hadron epoch, when matter was incredibly dense and weak interactions were still relatively frequent, neutrinos remained in thermal equilibrium with other particles. Around 1 second after the Big Bang, when temperature dropped to about 10 to the 10 Kelvin, neutrinos decoupled from the rest of matter. At this temperature, the universe's expansion rate exceeded the rate at which neutrinos interacted with other particles. Neutrinos stopped colliding with protons, neutrons, and electrons. They began traveling freely through space, forming what's called the cosmic neutrino background. This neutrino background still exists today, filling the universe just as the cosmic microwave background does. However, detecting it remains beyond current technology. Neutrinos that decoupled 1 second after the Big Bang have cooled to about 2 Kelvin, due to cosmic expansion. These cold neutrinos pass through us constantly, but interact so rarely that even the most sensitive detectors cannot observe them yet. Future experiments may eventually detect the cosmic neutrino background, providing another window into the universe's first second. The Hadron epoch also saw the continued annihilation of particle-antiparticle pairs. Protons and antiprotons annihilated when they met, as did neutrons and antineutrons. By the epoch's end, essentially all antiprotons and antineutrons had annihilated. The small excess of matter over antimatter, established much earlier, meant that matter survived. If matter and antimatter had been created in exactly equal amounts, the universe after the Hadron epoch would have contained only photons and neutrinos. No atoms, no stars, no galaxies, no life. Electrons and positrons also filled the universe during the Hadron epoch. These leptons existed in enormous numbers, converting freely to and from photons through pair creation and annihilation. An electron and positron could annihilate into 2 photons. 2 sufficiently energetic photons could collide and produce an electron-positron pair. At high temperatures, both processes occurred constantly, maintaining equilibrium between leptons and photons. As temperature dropped toward 10 to the 10 Kelvin, corresponding to an energy around 1 mega-electron volt, conditions approached the threshold for electron-positron pair creation. Below this energy, photons could no longer produce electron-positron pairs efficiently. electrons and positrons began annihilating without being replaced. This annihilation added energy to the photon bath, slightly reheating the photons relative to neutrinos, which had already decoupled and didn't share in this energy injection. The difference in temperature between photons and neutrinos after electron-positron annihilation has observable consequences. When astronomers measure the cosmic microwave background today, its temperature is about 2.7 Kelvin. The cosmic neutrino background, which hasn't interacted since 1 second after the Big Bang, should have a temperature of about 1.95 Kelvin. This temperature difference reflects the energy that photons gain from electron-positron annihilation, while neutrinos coasted along independently. By the end of the Hadron epoch, approximately 1 second after the Big Bang, the universe had simplified considerably. Nearly all unstable hadrons had decayed. Antiprotons and antineutrons had annihilated. Positrons and electrons had mostly annihilated, leaving only enough electrons to balance the charge of remaining protons. Neutrinos had decoupled and begun their free journey through space. The stage was set for the next major development, the formation of the first atomic nuclei through nuclear fusion. The Hadron epoch represents a transition from exotic physics dominated by conditions we can barely recreate experimentally to nuclear physics that we understand quite well. While we can create quark-gluon plasma for fleeting instants, the Hadron epoch's conditions, protons, neutrons, electrons at temperatures of billions of Kelvin, fall within the realm studied in detail at laboratories around the world. Our confidence in understanding this epoch rests on solid experimental and theoretical foundations. At roughly 1 second after the Big Bang, the universe stood ready for one of the most consequential processes in cosmic history, Big Bang nucleosynthesis. Temperature had dropped to about 10 billion Kelvin, and density had decreased to roughly 100 grams per cubic centimeter, still far denser than any matter we encounter in everyday life, but sufficiently dilute that nuclear reactions could proceed without being immediately disrupted by subsequent collisions. For nuclear fusion to occur, atomic nuclei must overcome their mutual electrical repulsion. All nuclei carry positive charge due to their protons. Like charges repel, creating an energy barrier that prevents nuclei from getting close enough for the strong nuclear force to bind them together. This barrier can be overcome in two ways: by collisions at high temperature, where particles move fast enough to smash through the barrier, or by quantum tunneling, where particles essentially sneak through the barrier without possessing sufficient classical energy. At 1 second after the Big Bang, temperature remained high enough that nuclei collided with sufficient energy to fuse. However, the universe was also expanding and cooling rapidly. This created a narrow window, lasting only a few minutes, during which conditions remained suitable for nuclear fusion. Before this window, the universe was too hot and collisions too violent for nuclei to remain bound. After this window, the universe had become too cool for fusion to occur at significant rates. The first step in nucleosynthesis involved the fusion of protons and neutrons to form deuterium, an isotope of hydrogen containing 1 proton and 1 neutron. Deuterium formation faced a challenge called the deuterium bottleneck. At temperatures above about 1 billion Kelvin, deuterium nuclei formed through proton-neutron collisions, but were immediately photodissociated, broken apart by high-energy photons that were abundant in the hot photon bath. The universe expanded and cooled below 1 billion Kelvin. Photons lost energy. Eventually, most photons became too weak to break deuterium apart. This occurred around 3 minutes after the Big Bang. At this point, deuterium could accumulate, opening the way for subsequent fusion reactions. Once deuterium existed in significant quantities, further fusion proceeded rapidly. Deuterium nuclei could collide with protons to form helium-3, an isotope with 2 protons and 1 neutron. Deuterium could also fuse with other deuterium nuclei, producing either helium-3 or tritium. Hydrogen-3 with 1 proton and 2 neutrons. Helium-3 and tritium could then fuse to form helium-4, the most tightly bound light nucleus. Helium-4 formation dominated nucleosynthesis because this nucleus is exceptionally stable. Its binding energy per nucleon exceeds that of all lighter nuclei. Once formed, helium-4 was unlikely to be destroyed. Nearly all neutrons that hadn't decayed ended up incorporated into helium-4 nuclei. Since the neutron-to-proton ratio at the start of nucleosynthesis was about 1:7, and each helium-4 nucleus contains 2 protons and 2 neutrons, roughly 1 helium-4 nucleus formed for every 12 hydrogen nuclei. This leads to a prediction. The universe should contain about 25% helium-4 by mass. 12 hydrogen nuclei, essentially 12 protons, since hydrogen nuclei are just single protons, have 12 times the proton mass. 1 helium-4 nucleus has 4 times the proton mass. The ratio gives 25% helium by mass. Observations confirm this prediction remarkably well. Everywhere astronomers look, primordial gas clouds contain about 25% helium-4, regardless of their location or age. Small amounts of other light nuclei also formed. Some deuterium survived without fusing further, leaving trace amounts that we detect in the universe today. Helium-3 also remained, constituting a small fraction of cosmic helium. Lithium-7 formed in tiny quantities through several reaction chains. These trace elements provide additional tests of nucleosynthesis theory. Critically, nucleosynthesis stopped at light elements. Attempts to build heavier nuclei faced insurmountable obstacles. First, the expanding universe cooled too quickly. Within about 20 minutes after the Big Bang, temperature dropped below levels where fusion could continue. Second, no stable nuclei exist, with mass numbers 5 or 8. Fusing helium-4 with a proton produces an unstable lithium-5 nucleus that immediately decays. Fusing 2 helium-4 nuclei produces beryllium-8, which also decays almost instantly. These gaps in the stability chart prevented nucleosynthesis from proceeding to heavier elements. All elements heavier than lithium formed later, inside stars. Stars spend millions or billions of years fusing hydrogen into helium, helium into carbon, and so on up the periodic table. Supernovae produce the heaviest elements through explosive nucleosynthesis. But during the first few minutes after the Big Bang, only hydrogen, helium, and traces of lithium formed. The agreement between predicted and observed abundances of light elements stands as one of cosmology's greatest triumphs. By understanding nuclear physics and applying it to conditions in the early universe, physicists predicted the cosmic abundances of deuterium, helium-3, helium-4, and lithium-7. Observations confirm these predictions to high precision. This concordance provides powerful evidence that our understanding of the universe's first few minutes is fundamentally correct. Neutrinos played a subtle but important role in nucleosynthesis. The number of neutrino types affects the expansion rate of the early universe. More neutrino types means more energy density from neutrinos, which speeds expansion. Faster expansion means the universe cools more quickly, giving less time for helium to form. By measuring helium abundance precisely and comparing to theoretical predictions, physicists have determined that exactly 3 types of light neutrinos exist. This conclusion, derived from cosmology, matches particle physics experiments that count neutrino types directly, a beautiful consistency between two completely different approaches. Small variations in the baryon density, the amount of ordinary matter, also affect nucleosynthesis outcomes. Higher baryon density means more frequent collisions, which tends to convert deuterium into heavier nuclei more efficiently. By measuring the abundances of different light elements, especially the deuterium to hydrogen ratio, astronomers can infer the baryon density of the universe. This measurement agrees with independent determinations from the cosmic microwave background, again demonstrating the internal consistency of cosmological theory. By about 20 minutes after the Big Bang, nucleosynthesis had essentially finished. The universe contained roughly 75% hydrogen by mass and 25% helium, with trace amounts of deuterium, helium-3, and lithium-7. No heavier elements existed yet. These proportions would remain essentially unchanged until the first stars formed hundreds of millions of years later and began forging heavier elements in their cores. The first second's events, matter-antimatter asymmetry, neutron-proton freeze-out, neutrino decoupling, determined what happened during nucleosynthesis. The neutron abundance fixed helium production. The photon-to-baryon ratio influenced deuterium survival. The expansion rate set the duration of the nucleosynthesis window. Everything connected through chains of cause and effect stretching back to the universe's earliest moments. We've traced the universe through its opening second, moving from the Planck epoch through grand unification, inflation, electroweak symmetry breaking, quark confinement, and Hadron evolution, arriving at the threshold of nucleosynthesis. Each epoch built upon the previous one, establishing conditions for subsequent developments. During the Planck epoch, quantum gravity effects dominated, and our current theories struggle to provide reliable descriptions. Grand unification saw three forces operating as one, with X and Y bosons creating the matter-antimatter asymmetry essential for our existence. Inflation stretched a microscopic region to cosmic scales, smoothing space to flatness and imprinting quantum fluctuations that would seed all future structure. The electroweak phase transition separated electromagnetism from the weak force and gave mass to fundamental particles through the Higgs mechanism. The quark epoch maintained matter in a plasma state until confinement bound quarks into hadrons. The Hadron epoch saw neutrinos decouple, electrons and positrons annihilate, and neutrons begin their decay that would influence helium production. Everything emerged from that first second. The forces governing nature, the masses of particles, the matter dominating over antimatter, the seeds of galaxies, the proportions of light elements. The universe at 1 second old contained all the ingredients necessary to evolve into the cosmos we observe today. Before continuing with later epochs, we should reflect on what time means during the universe's earliest moments. We've described events as occurring at specific times, 10 to the negative 43 seconds, 1 microsecond, 1 second. But time itself represents a subtle concept, especially near the beginning of the universe. In everyday experience, time flows steadily forward. 1 second equals 1 second everywhere and always. However, Einstein's general relativity revealed that time is relative. Clocks tick at different rates depending on gravity and motion. Near a black hole, time slows dramatically compared to distant regions. An observer falling toward a black hole ages differently than one remaining safely away. During the Planck epoch, space-time itself fluctuated quantum mechanically. The notion of a smoothly flowing time parameter breaks down. We can't meaningfully say what happened at time zero in the same way we describe what happens at 3 o'clock on a Tuesday. The structure of time itself may have been indeterminate, subject to quantum uncertainty. Some theories propose that time emerged gradually as a meaningful concept, rather than existing from the outset. Inflation complicates temporal descriptions further. During exponential expansion, different regions of space experience time at different effective rates. A region that inflated longer exists in a different temporal state than one where inflation ended earlier. The concept of a universal time coordinate, one that ticks at the same rate everywhere, becomes problematic during inflation. Physicists often use conformal time rather than standard time when describing the early universe. Conformal time accounts for the expansion of space, providing a coordinate system better suited to cosmology. In conformal time, light always travels at 45-degree angles on space-time diagrams, simplifying calculations. However, conformal time differs from time measured by physical clocks, requiring care in interpretation. Temperature serves as another time coordinate in early universe physics. As the universe expands, it cools predictably. Specifying temperature essentially specifies time. Saying, when temperature was 10 to the 15 Kelvin, is equivalent to saying at 10 to the negative 12 seconds. Scientists often use temperature because it directly relates to the energies of particles, making the physics more intuitive. The question of what happened before the Big Bang challenges our understanding of time. If time itself began with the Big Bang, then before becomes meaningless, like asking what's north of the North Pole. Some theories, however, suggest the Big Bang was not the ultimate beginning, but rather a transition from a previous state. In eternal inflation models, our universe budded off from an eternally inflating background. In cyclic models, the universe undergoes repeated expansions and contractions. In these scenarios, time extends before our Big Bang. Quantum cosmology takes another approach. In the Hartley-Hawking no-boundary proposal, time becomes space-like near the Big Bang. The universe has no boundary in time, no actual moment of creation, but rather smoothly transitions from a Euclidean regime where time behaves geometrically, like a spatial dimension. Asking what came before becomes like asking what lies south of the South Pole. Once you recognize that south loses meaning at that point. These deep questions about time's nature remain unresolved. Different theoretical approaches suggest different answers. What we can say with confidence is that time, as measured by clocks, has been ticking for approximately 13.8 billion years since the hot Big Bang state began. Whether this represents the absolute beginning of time or simply a phase transition in a longer history remains uncertain. For our purposes, describing events in the first second, standard time coordinates work adequately. We can meaningfully discuss processes at 1 microsecond versus 1 millisecond, even if the ultimate nature of time during the Planck epoch remains mysterious. The physics we've described, particle interactions, phase transitions, expansion dynamics, operates within a framework where time flows forward consistently, even if the deepest questions about time's origin remain open. Throughout our journey through the first second, we've referenced temperatures reaching 10 to the 32 Kelvin and dropping to 10 to the 10 Kelvin. These numbers merit deeper consideration. What does temperature mean in the early universe, and why did it decrease so dramatically? Temperature measures the average kinetic energy of particles. In a gas, hotter temperatures mean particles move faster on average. In the early universe, temperature determined which particles could exist and which reactions could occur. High temperatures meant high particle energies, allowing the creation of massive particles and driving reactions in both directions. As temperature dropped, heavy particles could no longer be created, and some reactions became too slow to maintain equilibrium. The universe cooled because it expanded. This connection follows from thermodynamics and general relativity. As space expands, the volume containing any given amount of energy increases. Energy, density, energy per unit volume, therefore decreases. For radiation like photons, this decreases both the number density and the energy of individual photons. Photons get redshifted by expansion, their wavelengths stretching as space expands, reducing their energy proportionally. The mathematical relationship between expansion and temperature is straightforward. Temperature decreases inversely with the scale factor, a measure of how much the universe has expanded. If the universe doubles in size, temperature drops by half. If the universe expands by a factor of 1,000, temperature drops by a factor of 1,000. This simple relationship held throughout the first second and continues to hold today. During the first second, the universe expanded enormously. At the Planck time, the universe was incomprehensibly tiny, perhaps 10 to the negative 35 meters across, for the region that would become our visible universe today. By 1 second, this region had expanded to roughly a few light seconds across, a few billion kilometers. This expansion factor of perhaps 10 to the 26 or more caused temperature to plummet from Planck values to 10 billion Kelvin. The energy content of the universe shifted dramatically during this expansion. At the earliest moments, the universe's energy consisted primarily of the potential energy in quantum fields, the inflaton field during inflation, the Higgs field during electroweak symmetry breaking. When these fields transitioned to lower energy states, their potential energy converted into kinetic energy of particles, heating the universe through reheating events. After inflation, the universe's energy existed primarily as radiation, photons and relativistic particles moving near light speed. Radiation dominated over matter in the early universe. Matter particles existed, but the universe's total energy budget was dominated by photons, neutrinos, and other relativistic particles. This radiation-dominated era lasted until the universe was roughly 50,000 years old. During radiation domination, the universe's expansion rate depends on radiation density. Einstein's equations link the expansion rate, measured by the Hubble parameter, to energy density. Higher density means faster expansion. As radiation density decreased through expansion, the expansion rate slowed. This self-regulating behavior characterized the universe's evolution after inflation ended. The equivalence between mass and energy, expressed in Einstein's famous equation E equals mc squared, becomes particularly relevant in the early universe. At high temperatures, particles and antiparticles, constantly created from pure energy and annihilated back into energy. The distinction between matter and radiation blurred. A photon with sufficient energy could materialize as an electron-positron pair. Those particles could annihilate back into photons. Mass and energy converted freely, maintaining thermal equilibrium. Only when temperature dropped below a particle's mass energy did that particle stop being created thermally. The top quark, with a mass energy of about 175 giga-electron-volts, ceased being produced thermally when temperature dropped below about 2 trillion Kelvin. The Higgs boson, with mass around 125 giga-electron-volts, likewise disappeared from the thermal bath as temperature fell below about 10 to the 15th Kelvin. Each particle type froze out when its mass energy exceeded typical collision energies. The photon to baryon ratio, the number of photons for every proton or neutron, provides another important quantity. Today, this ratio is about 1 billion to 1. For every atom in the universe, roughly 1 billion cosmic microwave background photons exist. This ratio was established during the first second and has remained essentially constant ever since, apart from slight changes during nucleosynthesis, when electron-positron annihilation added energy to photons. This huge photon-to-baryon ratio reflects the tiny matter-antimatter asymmetry created during the grand unification epoch. If matter and antimatter had been exactly equal, all baryons would have annihilated, leaving only photons and neutrinos. The 1 part in 1 billion excess of matter over antimatter meant that after annihilation, 1 baryon survived for every billion photons. This sets the baryon density relative to radiation density, which influences everything from nucleosynthesis outcomes to when matter began dominating over radiation gravitationally. Entropy provides yet another perspective on the early universe's evolution. Entropy measures disorder, or more precisely, the number of possible microscopic states consistent with macroscopic observations. The second law of thermodynamics states that entropy always increases or remains constant, never decreases. In the expanding universe, entropy increases primarily through the increase in volume. The number of possible locations and momentum states for particles grows as space expands. However, the entropy per unit volume, or entropy density, decreases. Total entropy increases while entropy density decreases. Both statements are true simultaneously and don't contradict each other. During inflation, something remarkable happened with entropy. The exponential expansion diluted away any pre-existing entropy to negligible levels. Then reheating created enormous amounts of entropy as field energy converted into particles. Nearly all the entropy in our observable universe was generated during the reheating that ended inflation. This entropy has been spreading through an ever larger volume ever since. The arrow of time, the fact that processes proceed forward rather than backward, connects to entropy. We perceive time as flowing forward because entropy increases. Eggs break but don't spontaneously reassemble. Coffee cools but doesn't spontaneously heat up. These everyday experiences reflect entropy increase. In the early universe, despite enormous energy densities and violent conditions, the same arrow of time held. Entropy increased as the universe expanded, giving time its direction. All these concepts, temperature, energy density, expansion rate, entropy, interconnect through physics. Changes in one quantity necessitate changes in others. The universe's evolution through the first second represents a coherent story where each development follows naturally from previous conditions. The mathematics describing these processes, while complex, rests on well-established physical principles tested extensively in laboratories. The concept of symmetry and its breaking underlies much of what happened during the first second. When physicists speak of symmetry, they mean that a system remains unchanged under certain transformations. A sphere looks the same when rotated. It has rotational symmetry. Physical laws exhibit various symmetries that constrain their form and provide deep insights into nature. Gauge symmetries govern fundamental forces. The electromagnetic force exhibits a gauge symmetry related to phase transformations of quantum fields. This symmetry requires the existence of photons and dictates how photons interact with charged particles. The strong force has its own gauge symmetry, called color symmetry, which requires gluons and determines their interactions with quarks. The weak force also involves gauge symmetry, as does gravity in the framework of general relativity. During the Planck epoch, physicists suspect that a fundamental symmetry unified all forces. This ultimate symmetry remained unbroken, and all interactions arose from a single underlying principle. As the universe cooled, this symmetry broke in stages, separating forces sequentially. Each symmetry breaking represented a phase transition where the universe's state changed fundamentally. Spontaneous symmetry breaking provides the mechanism. Consider a ball balanced perfectly atop a hill. The situation is symmetric. The ball could roll down in any direction. However, this symmetric state is unstable. Eventually, the ball rolls down one particular direction, breaking the symmetry. After rolling down, the symmetry is hidden rather than destroyed. The hill still looks the same from all sides, but the ball's final position singles out one direction. The Higgs field underwent spontaneous symmetry breaking during the electroweak phase transition. At high temperatures, the Higgs field sat at zero value, a symmetric state where electromagnetism and the weak force remained unified. As temperature dropped, this symmetric state became unstable. The Higgs field rolled to a non-zero value, spontaneously breaking the symmetry and separating the electromagnetic and weak forces. When symmetry breaks, certain particles acquire mass. Before symmetry breaking, symmetry principles required those particles to be massless. After breaking, the Higgs field's non-zero value gives particles mass proportional to how strongly they couple to the field. This explains why W and Z bosons are heavy, while photons remain massless. Photons don't couple to the Higgs field, while W and Z bosons do. Symmetry breaking also explains the four fundamental forces' different strengths. At high energies during the grand unification epoch, the electromagnetic, weak, and strong forces had equal strength. They were unified. After symmetry breaking separated them, each force acquired its own characteristic strength. The strong force became strong, the electromagnetic force intermediate, and the weak force weak. These differing strengths reflect the details of how symmetry broke rather than fundamental differences between the forces. The process of symmetry breaking generally releases energy. When water freezes, latent heat is released. The energy that kept molecules moving freely in liquid form gets expelled as the molecules lock into ice's rigid structure. Similarly, when the Higgs field settled into its non-zero value, energy was released. This energy might have driven processes like inflation, or contributed to reheating events. Topological defects can form during symmetry breaking. These are stable configurations of fields, analogous to knots in rope, that cannot be smoothed away. Magnetic monopoles represent one type of topological defect that should form when the strong force separated from the electroweak force. Cosmic strings, linear concentrations of field energy, might form during other phase transitions. Domain walls, another defect type, could also arise under certain circumstances. The absence of observed topological defects creates challenges for some theories. We don't see magnetic monopoles despite predictions they should exist. Inflation potentially solves this by exponentially diluting any monopoles formed before inflation to densities far below detectability. However, if monopoles formed after inflation, we should observe them. Their absence constrains both grand unified theories and inflation models. Symmetries also explain particle families. Quarks come in 6 types grouped into 3 generations. Leptons likewise appear in 3 generations. This pattern reflects symmetries in how particles transform into each other. The standard model doesn't explain why 3 generations exist, but whatever deeper theory extends, the standard model will likely reveal additional symmetries accounting for this structure. CP symmetry, combining charge conjugation, swapping particles with antiparticles, and parity, mirror reflection, relates closely to the Hume matter-antimatter asymmetry. If CP symmetry held perfectly, equal amounts of matter and antimatter would exist. The universe exhibits CP violation, meaning processes don't occur identically when particles are swapped with antiparticles and everything is mirror reflected. This violation, necessary for generating matter-antimatter asymmetry, itself represents a form of broken symmetry. Physicists seek a theory of everything, an ultimate theory that unifies all forces and explains all particles within a single symmetric framework. String theory and other approaches attempt this unification. In these theories, particles represent different vibration modes of fundamental strings or branes, and forces arise from different ways these objects interact. The early universe, at Planck energies, would have exhibited the full symmetry of this ultimate theory. Everything we observe today represents a low-energy shadow of that symmetric perfection, altered by successive symmetry breakings as the universe cooled. Whether we ever develop a complete theory of everything remains uncertain. The energies required to test such theories exceed anything achievable at particle accelerators by many orders of magnitude. However, the universe itself serves as the ultimate laboratory. By studying conditions during the first second, we probe energy regimes that reveal hints of ultimate unification. Each observation of the cosmic microwave background, each precision measurement of particle properties, each detection of gravitational waves provides another piece of evidence constraining theoretical possibilities. Quantum mechanics governed every process during the first second. At the energies and densities present, classical physics, the physics of everyday objects, completely fails. Particles behave as both particles and waves, existing in superpositions of multiple states simultaneously. Uncertainty principles limit how precisely we can know complementary properties. Virtual particles pop in and out of existence. Understanding the first second requires understanding quantum mechanics. Wave-particle duality means that objects exhibit both wave-like and particle-like properties depending on how they're observed. Photons sometimes behave as waves, creating interference patterns. Other times, they behave as discrete particles, absorbed or emitted individually. This duality extends to all particles. Electrons, protons, quarks, all exhibit wave properties under appropriate circumstances. During the first second, particles' wave nature was pronounced. At high temperatures, thermal, wavelengths, the typical quantum wavelength of particles in a thermal bath, become comparable to particle spacings. Waves from different particles overlap and interfere. The plasma of particles acted quantum mechanically as much as it acted classically. The uncertainty principle places fundamental limits on knowledge. We cannot simultaneously know both the position and momentum of a particle with arbitrary precision. The more precisely we determine one, the less precisely we can know the other. During the Planck epoch, this uncertainty extended to spacetime itself. We cannot specify exactly when and where events occurred below the Planck scale, because the concepts of space and time become quantum mechanically uncertain. Quantum fluctuations, temporary violations of energy conservation allowed by uncertainty, become significant when durations are brief or volumes are small. During inflation, quantum fluctuations in the inflaton field were stretched to cosmic scales. These fluctuations, originally microscopic and quantum, became macroscopic density variations that later collapsed into galaxies. This represents a profound connection between the quantum and cosmic domains. Virtual particles represent another quantum phenomenon. In quantum field theory, the vacuum isn't truly empty, but seethes with particle-antiparticle pairs constantly creating and annihilating. These pairs exist too briefly to observe directly, but affect measurable quantities. During the first second, virtual particles were everywhere, and the distinction between virtual and real particles blurred at high energies. Tunneling allows particles to pass through energy barriers they classically couldn't surmount. During nucleosynthesis, quantum tunneling helped protons fuse despite their electrical repulsion. Without tunneling, fusion would require even higher temperatures. During the Electroweak transition, tunneling might have allowed bubbles of the new phase to nucleate within the old phase, driving the transition forward. Quantum entanglement connects particles in ways that defy classical intuition. Measuring one particle instantaneously affects the state of another, regardless of separation. During the first second, particles that interacted became entangled. As space expanded, these entangled particles separated to vast distances while maintaining correlations. Today, photons in the cosmic microwave background may retain quantum correlations established during the first second, though detecting such correlations remains experimentally challenging. The measurement problem in quantum mechanics, how observation collapses quantum superpositions into definite states, becomes peculiar in cosmology. In laboratory quantum mechanics, we distinguish between the quantum system being measured and the classical apparatus doing the measuring. But for the universe as a whole, everything is quantum. There's no external observer or classical domain. How then do quantum probabilities become actual outcomes? Various interpretations address this question. The Copenhagen interpretation posits that observation causes collapse, but struggles to define observation in a cosmological context. The many worlds interpretation suggests that all quantum possibilities occur, with the universe branching into different versions corresponding to each outcome. Decoherence theory proposes that interactions with the environment cause apparent collapse without requiring a conscious observer. For practical purposes, physicists calculate probabilities using quantum field theory and compare predictions to observations. These calculations work extraordinarily well. Quantum chromodynamics predictions for the quark-Hadron transition match observations from heavy ion collisions. Electroweak theory predictions match particle accelerator results to astonishing precision. Whether or not we fully understand quantum measurement philosophically, the mathematical apparatus reliably describes physical processes. Quantum field theory combines quantum mechanics with special relativity. In this framework, fields permeate space, and particles represent excitations of these fields. Interactions occur when field excitations influence each other. This mathematical structure underlies the standard model of particle physics, which describes all known particles and forces except gravity. During the first second, quantum field theory governed every interaction. Quarks exchanged gluons through quantum chromodynamics. Leptons interacted via electroweak bosons. The Higgs field permeated space, giving particles mass. All these processes arose from quantum fields evolving according to field equations. The universe's evolution represents a quantum field theory calculation writ large across spacetime. Gravity remains the holdout. We lack a complete quantum theory of gravity. General relativity describes gravity beautifully at large scales, but treats spacetime classically. Quantum mechanics describes particles and fields precisely, but struggles with gravity's geometric nature. Unifying these frameworks, developing quantum gravity remains theoretical physics' greatest challenge. String theory and loop quantum gravity represent the leading approaches to quantum gravity. String theory proposes that fundamental constituents are one-dimensional strings whose vibrations correspond to different particles. Gravity arises naturally in string theory, potentially solving the quantization problem. Loop quantum gravity takes a different approach, quantizing space-time geometry directly. Both theories make predictions about Planck scale physics, but testing these predictions remains beyond reach. For most of the first second, the lack of complete quantum gravity doesn't cause problems. Only during the Planck epoch, when gravity and quantum mechanics equally dominated, does quantum gravity become essential. From the grand unification epoch onward, gravity was weak, enough compared to other effects that treating it classically suffices. This fortunate circumstance allows us to describe most of the first second confidently despite lacking ultimate quantum gravity theory. How do we know what happened during the first second? We can't directly observe events 13.8 billion years ago. We can't recreate Planck-scale conditions in laboratories. Yet physicists speak confidently about temperatures, densities, and processes during those earliest moments. What evidence supports these claims? Multiple lines of evidence, each independently pointing to the same conclusion, build confidence. No single observation proves the entire story, but the cumulative case becomes compelling. Each prediction that matches observation strengthens our trust in the theoretical framework. The cosmic microwave background provides the most direct observational window. This radiation, released when the universe was 380,000 years old, carries imprints from earlier epochs. Temperature fluctuations measured across the sky match predictions from inflation-generated quantum fluctuations. The slight variations, about 1 part in 100,000, have exactly the statistical properties inflation predicts. The pattern of these fluctuations depends on conditions during the first second. The photon-to-baryon ratio, established through matter-antimatter asymmetry, affects how acoustic waves propagated in the early plasma. The neutrino density, determined when neutrinos decoupled 1 second after the Big Bang, influenced how quickly the universe expanded. By measuring the cosmic microwave background in exquisite detail, satellites like WMAP and Planck have verified predictions about the first second with percent-level precision. Light element abundances provide independent confirmation. The amount of helium-4, deuterium, helium-3, and lithium-7 in the universe depends critically on conditions during Big Bang nucleosynthesis, which in turn depends on earlier epochs. The neutron-to-proton ratio, set by weak interaction freeze-out during the Hadron epoch, determines helium abundance. The baryon density, established earlier, affects deuterium production. Astronomers measure these abundances by observing ancient, pristine gas clouds that haven't been contaminated by stellar processing. The measured values match theoretical predictions remarkably well. This agreement confirms our understanding of nuclear physics and demonstrates that the universe indeed passed through the hot, dense state described by Big Bang theory. Particle accelerator experiments test physics at energies comparable to those in the early universe. The Large Hadron Collider reaches collision energies around 14 tera-electron volts, roughly 10 to the 17 Kelvin. This corresponds to conditions when the universe was about 10 to the negative 15 seconds old during the Electroweak epoch. By recreating these conditions experimentally, we verify that our theories correctly describe particle behavior at such energies. The discovery of the Higgs boson confirmed electroweak symmetry breaking occurred as predicted. The measured mass of 125 giga-electron-volts matches theoretical expectations. The boson's decay patterns and interaction rates agree with standard model predictions. These observations validate our understanding of the electroweak phase transition during the first second. Heavy ion collision experiments at RHIC and the LHC create quark-gluon plasma, the state of matter that filled the universe during the quark epoch. By studying this plasma's properties, physicists verify theoretical predictions about quark confinement and hadronization. The plasma's viscosity, temperature dependence, and transition to hadronic matter all match theoretical expectations, confirming our picture of the quark epoch. Precision measurements of particle properties constrain early universe physics. The electron's mass, the proton's charge, the fine structure constant. These fundamental parameters were set during the first second through processes we've described. That our measured values remain consistent across different experiments and observations suggests we understand how these parameters originated. Neutrino observations provide additional evidence. The detection of neutrinos from the Sun and from supernovae demonstrates that neutrinos exist and behave as predicted. Solar neutrino experiments revealed that neutrinos oscillate between different types, confirming they have mass. The measured properties of neutrinos constrain cosmological models. The neutrino mass density affects cosmic structure formation, and observations of galaxy clustering limit how heavy neutrinos can be. Gravitational wave detection opens a new observational window. While we haven't yet detected primordial gravitational waves from inflation or phase transitions, the successful observation of gravitational waves from merging black holes and neutron stars confirms that space-time ripples propagate as general relativity predicts. Future detectors may observe signals from the first second, providing direct evidence of early universe dynamics, the universe's large-scale structure, how galaxies cluster into walls and voids, also traces back to the first second. The quantum fluctuations inflated to cosmic scales became the seeds around which matter gravitationally clustered. Statistical properties of galaxy distribution match predictions based on inflation remarkably well. The power spectrum of density fluctuations measured from galaxy surveys agrees with theoretical calculations to high precision. Dark matter's existence, inferred from galaxy rotation curves and gravitational lensing, connects to the first second as well. Whatever dark matter consists of, likely some undiscovered particle, its abundance was set during the early universe. If dark matter particles were created thermally and then froze out when the universe cooled, their present density depends on their mass and interaction strength. Observations of dark matter density constrain these properties, providing clues about what happened when dark matter particles decoupled from the thermal bath. Each of these observations, cosmic microwave background, light element abundances, particle accelerator results, neutrino detections, gravitational waves, large-scale structure, dark matter, represents an independent test. That all tests give consistent results, all pointing to the same story about the first second, provides strong confidence in our theoretical framework. Importantly, these observations reveal not just that something happened, but specific details about what happened. We don't merely know the universe was hot and dense. We know the temperature and density at specific times. We don't just infer that symmetry breaking occurred. We measure the energy scale at which it happened. The agreement between theory and observation extends to quantitative details, not merely qualitative features. Despite substantial progress, significant uncertainties remain about the first second. Some questions await better observations or experiments. Others may require theoretical breakthroughs. A few might prove unanswerable with available evidence. The Planck epoch remains largely mysterious. Without a complete quantum gravity theory, we cannot confidently describe conditions during the first 10 to the negative 43 seconds. Different quantum gravity approaches make different predictions about what occurred. Some suggest space-time has a grainy structure at Planck scales. Others propose extra spatial dimensions. Still others indicate time itself emerged gradually rather than existing from the outset. Distinguishing between these possibilities requires observations we don't yet know how to make. Inflation theory, while successful at explaining observations, lacks fundamental derivation. We don't know what field served as the inflaton or what potential energy curve it followed. Many models fit observations equally well. Future measurements, particularly of gravitational waves from inflation, might narrow possibilities, but currently, uncertainty remains about inflation's specific mechanism. Whether inflation occurred at all remains debatable. While most cosmologists favor inflation, alternatives exist. Some models achieve similar observational consequences through different mechanisms. Cyclic cosmology, where the universe bounces between expansion and contraction phases, can explain flatness and uniformity without inflation. Distinguishing definitively requires observations we haven't yet made. The matter-antimatter asymmetry's origin isn't fully resolved. While we know X and Y boson decays during the grand unification epoch could generate asymmetry, we can't directly test this mechanism. The standard model alone produces insufficient asymmetry. Physics beyond the standard model must contribute, but we don't know what that new physics is. Various theories propose different sources of additional CP violation, but experimental verification remains elusive. Dark matter's identity remains unknown. We've inferred its existence and measured its density, but we don't know what particles comprise it. Leading candidates include weakly interacting massive particles, axions, sterile neutrinos, or more exotic possibilities. If dark matter particles were created during the first second, their properties connect intimately to early universe physics, but without direct detection, we can't confirm this connection. Dark energy presents another mystery. This energy component, causing the universe's expansion to accelerate, might relate to the vacuum energy discussed in inflation contexts. However, the observed dark energy density is vastly smaller than theoretical predictions based on particle physics. This hierarchy problem, why dark energy is so much smaller than expected, remains unsolved. Whether dark energy connects to processes during the first second or represents something entirely different isn't clear. The cosmological constant problem relates to dark energy. Quantum field theory predicts that empty space should have enormous vacuum energy density, perhaps 10 to the 120 times larger than observed. Yet measurements show the actual vacuum energy is tiny. Why this dramatic suppression occurs remains unexplained. Understanding vacuum energy matters for comprehending the inflaton field and the Higgs field's behavior during the first second. The origin of structure's precise details remains incompletely understood. While we know quantum fluctuations during inflation's seeded structure, we don't know inflation's exact parameters. The amplitude and spectral index of primordial fluctuations while measured aren't predicted from first principles. A complete theory of inflation would calculate these values rather than treating them as free parameters. Baryogenesis, the process that created more matter than antimatter, might have occurred through mechanisms beyond those we've discussed. leptogenesis, where an asymmetry in leptons rather than quarks arose first, provides an alternative route. This asymmetry could then transfer to baryons through weak interactions. Testing leptogenesis requires understanding neutrino masses and interactions better than we currently do. Magnetic monopoles, if they exist, should have formed during phase transitions. Their absence in observations creates the monopole problem. Inflation dilutes monopoles exponentially, potentially explaining their absence. However, if monopoles somehow survived or formed after inflation, even tiny numbers might be detectable. Experiments search for them without success so far, but the question remains open. The value of the fine structure constant, the number characterizing electromagnetic interaction strength, isn't predicted by theory. Similarly, for quark and lepton masses, the Higgs field strength and other fundamental parameters. These numbers were set during the first second through symmetry-breaking processes, but we can't calculate their values from deeper principles. A theory of everything would presumably predict these parameters, but we lack such a theory. Why 3 generations of particles exist remains unexplained. Quarks come in 3 families, as do leptons. The standard model accommodates this pattern, but doesn't explain it. Theories beyond the standard model often predict additional structure, potentially accounting for 3 generations, but experimental confirmation is lacking. The hierarchy problem questions why the weak force's characteristic energy, 100 giga-electron-volts, is so much smaller than the grand unification energy, 10 to the 16 giga-electron-volts, or the Planck energy, 10 to the 19 giga-electron-volts. This huge separation of scales seems unnatural without some mechanism to maintain it. Supersymmetry and other theories attempt to address this, but experimental searches haven't confirmed these proposals. Whether the universe is finite or infinite remains uncertain. Observations show our visible universe is flat to high precision, suggesting total spacetime might be infinite. However, we only observe a finite region, the observable universe, bounded by how far light has traveled since the Big Bang. Topology of space beyond our horizon remains unknown. The universe might be finite but unbounded, like the surface of a sphere exists in 2 dimensions but has no edge. These uncertainties shouldn't diminish confidence in what we do know. The first second's broad outlines, rapid expansion and cooling, phase transitions separating forces, particle creation and annihilation, symmetry breaking, rest on solid theoretical and observational foundations. Details remain to be worked out, but the overall picture has proven robust across decades of testing and refinement. Beyond physics, the first second raises profound philosophical questions. Why does the universe exist at all? Why these physical laws rather than others? How does consciousness emerge in a universe governed by quantum fields and Einstein's equations? These questions stretch beyond science into philosophy, but they connect intimately to the first second's events. The question of why anything exists confronts every cosmological model. Even if we trace the universe back to a quantum fluctuation or describe it as eternal through inflation, we might still ask why quantum fields exist, why they follow particular equations, why spacetime provides their arena. Some philosophers suggest this question is unanswerable. Existence is brute fact requiring no explanation. Others propose that existence is necessary, that nothingness is actually impossible for logical reasons we don't yet grasp. The fine-tuning problem notes that many physical constants appear precisely calibrated to allow complex structures like stars, planets, and life. If the strong force were slightly stronger, fusion in stars would proceed too quickly. If the weak force were stronger, Big Bang nucleosynthesis would produce different light element ratios. If the Higgs field strength differed, atoms might not be stable. These coincidences seem remarkable. One response invokes the anthropic principle. We observe this universe because only universes with these properties generate observers. If countless universes exist with varying properties, a multiverse, we shouldn't be surprised to find ourselves in one of the rare universes where complexity arises. The anthropic principle doesn't explain why any universes exist, but it removes the surprise at finding ourselves in a seemingly special one. Eternal inflation naturally generates a multiverse. If inflation occurred, quantum fluctuations during inflation could spawn endless bubble universes, each potentially with different physical laws. Our observable universe represents one bubble in an infinite foam. The constants we measure, particle masses, force strengths, symmetry breaking scales, might vary between bubbles. We observe particular values because only certain combinations allow observers to emerge. Critics argue that multiverse theories aren't falsifiable. If we can't observe other universes, how can we test whether they exist? Proponents respond that the multiverse emerges naturally from well-tested physical theories like inflation and quantum mechanics. We should accept their consequences even if some aspects remain unobservable. The debate continues without resolution. The laws of physics themselves raise questions. Why does nature obey mathematical equations? Why does symmetry matter? Why do conservation laws hold? These questions probe deeper than specific theories, asking about the mathematical structure underlying reality. Some physicists and philosophers suggest mathematics isn't merely a tool for describing reality, but constitutes reality's fundamental nature. In this view, the universe is mathematical, and physical existence means existing as a solution to equations. Emergence represents another philosophical puzzle. How do high-level phenomena arise from low-level physics? The first seconds physics involves quantum fields and particles. Yet this led eventually to atoms, molecules, chemistry, biology, consciousness. At what point did genuinely new phenomena emerge that can't be reduced to particle physics? Is consciousness an emergent property of certain physical arrangements, or does it require something beyond physics? Reductionism holds that all phenomena ultimately reduce to fundamental physics. Understanding particles and forces suffices in principle to understand everything else. Anti-reductionists argue that higher levels of organization exhibit properties not predictable from lower levels, requiring new concepts and laws. The first second exemplifies extreme reductionism. Everything, reduced to quantum fields and space-time. Whether this reductionism extends to life and mind remains contentious. Time's arrow presents a philosophical puzzle related to entropy and the second law of thermodynamics. Physics equations generally work equally well forward or backward in time, yet we experience time flowing in one direction. Entropy provides the arrow. It increases forward in time. But why was entropy low at the Big Bang? This requires initial conditions. But what selected those conditions? Some theorists propose that the universe began in a maximum entropy state rather than minimum. If the Big Bang represented a fluctuation from equilibrium, the perceived arrow of time reflects our perspective. We exist during a rare low entropy fluctuation and naturally define forward as the direction entropy increases. This radical proposal remains speculative, but addresses deep questions about time's nature. The role of chance versus necessity also merits consideration. Did the first seconds events occur by necessity, determined by laws admitting no alternatives, or did chance play a role through quantum fluctuations and symmetry breaking? The outcome of symmetry breaking, which direction the Higgs field chose, might have been random, not predetermined. This suggests genuine randomness entered the universe's history, not merely apparent randomness due to ignorance. Quantum mechanics famously includes probabilistic elements. Before measurement, quantum systems exist in superpositions, and only probabilities can be predicted for measurement outcomes. Did this quantum randomness affect the first second meaningfully? Inflation stretching quantum fluctuations to cosmic scales suggests it did. The specific pattern of galaxies we observe might reflect quantum randomness during inflation, not inevitable consequence of initial conditions. The question of origins remains. Did the universe have a beginning, or has it existed eternally? If time began with the Big Bang, then before is meaningless. No prior state existed. If the Big Bang was a transition from a previous state, we push the question back without resolving it. Some cyclic models propose infinite sequences of expansions and contractions, avoiding an absolute beginning. Others suggest the universe spontaneously created itself through quantum effects, though how something emerges from nothing challenges intuition. Causality's role becomes subtle near the Big Bang. Normally, effects follow causes temporally. But if time itself began with the Big Bang, causal chains can't extend before it. Some physicists propose that the universe is its own cause, a self-generating bootstrap where later states causally influence earlier ones through quantum effects. This abandons linear causality, but might resolve how something arises from nothing. These philosophical questions lack definitive answers. Physics provides increasingly detailed descriptions of the first second, but cannot address why those descriptions apply, why existence occurs, or what consciousness means. The boundary between physics and philosophy remains permeable. As our scientific understanding deepens, some formerly philosophical questions become empirically tractable. Others remain firmly in philosophy's domain, possibly forever. The first second determined the universe's subsequent evolution, but that evolution took billions of years to reach the universe we inhabit today. Let's briefly trace the path from the first second to the present, highlighting major developments. After Big Bang nucleosynthesis concluded around 20 minutes, the universe continued expanding and cooling, but underwent no major transitions for nearly 400,000 years. The plasma of protons, electrons, and photons remained in thermal equilibrium. Photons scattered continuously off electrons, preventing light from traveling far. The universe was opaque, like fog on a dense morning. Around 380,000 years after the Big Bang, temperature dropped to about 3,000 Kelvin. At this point, electrons and protons combined to form neutral hydrogen atoms. This process, called recombination, marked a profound change. Neutral atoms don't scatter photons efficiently. Light could suddenly travel freely through space. The universe became transparent. The cosmic microwave background radiation comes from this epoch. Photons that scattered off electrons just before recombination have traveled through space ever since, carrying information about conditions at that time. We observe these photons today, redshifted by expansion to microwave wavelengths, forming the cosmic microwave background. This radiation provides our most direct observational window into the early universe. Following recombination, the universe entered the Dark Ages, a period lasting several 100 million years when no stars yet existed. The universe contained only neutral hydrogen and helium gas, dark matter, and the fading radiation from the Big Bang. Gravity slowly pulled matter into denser regions, amplifying density contrasts established during inflation. The first stars formed roughly 100 to 200 million years after the Big Bang. These population 3 stars consisted of pure hydrogen and helium, with no heavier elements. They were likely massive and short-lived, fusing hydrogen to helium rapidly and then exploding as supernovae. These explosions synthesized the first heavier elements, carbon, oxygen, silicon, iron, seeding the universe with the chemical complexity necessary for planets and life. Early galaxies assembled through gravitational collapse and mergers. Small protogalaxies formed first, then merged to create larger structures. The first galaxies appeared perhaps 400 million years after the Big Bang. These early galaxies were smaller and more irregular than modern galaxies, but they contained young stars forming at prodigious rates. Ionization occurred when ultraviolet light from early stars and galaxies ionized the neutral hydrogen pervading space. This process, completing around 1 billion years after the Big Bang, returned much of the universe's hydrogen to ionized form. Unlike the earlier ionization during the hot Big Bang, this resulted from stellar activity rather than high temperature. Over subsequent billions of years, galaxies continued growing and evolving. Supermassive black holes formed in galaxy centers. Spiral and elliptical galaxy types emerged. Cosmic structure on the larger scales, galaxy clusters, superclusters, filaments and voids, became apparent as gravity organized matter hierarchically. Our Milky Way galaxy formed over billions of years through mergers and accretion. The oldest stars in our galaxy date to roughly 13 billion years ago, less than 1 billion years after the Big Bang. The Sun formed much later, about 4.6 billion years ago, from a collapsing molecular cloud enriched with heavy elements from previous stellar generations. Earth formed shortly after the Sun from material in the protoplanetary disk. Life emerged on Earth within the first 1 billion years of its existence. Evolution proceeded through single-celled organisms to complex multicellular life, eventually producing intelligent observers capable of reconstructing the universe's history. Throughout this evolution, the seeds planted during the first second guided development. The matter-antimatter asymmetry ensured atoms existed to form structures. The density fluctuations from inflation determined where galaxies formed. The light element abundances from nucleosynthesis provided the raw materials for chemistry. The forces and particles established through symmetry breaking governed how matter interacted. The universe continues evolving today. Expansion continues, now accelerating due to dark energy. Stars continue forming in some galaxies, while others have exhausted their gas supplies. Galaxies continue merging, with our Milky Way destined to collide with Andromeda Galaxy in several billion years. Black holes continue growing as they accrete matter. Looking to the far future, current understanding suggests the universe will expand forever. Accelerated expansion will eventually push distant galaxies beyond our observational horizon. Star formation will gradually cease as gas supplies deplete. Stars will burn out, leaving behind white dwarfs, neutron stars, and black holes. After unimaginable timescales, even black holes will evaporate through Hawking radiation. The universe approaches a cold, dark, dilute state. Yet this distant future, like the immediate present, traces causally to the first second. Everything emerged from that brief interval when the universe was hottest, densest, and most energetic. The laws governing the universe's ultimate fate are the same laws established during the first second. The 4 fundamental forces, the masses of particles, the constants of nature, all set during that opening moment, determine the universe's entire history from beginning to end. We've journeyed through the universe's opening second, from the Planck epoch through nucleosynthesis. Each fraction of that second saw transformations that shaped everything to follow. Forces separated, symmetries broke, particles acquired mass, matter dominated over antimatter, quantum fluctuations grew to cosmic scales. In that brief instant, the universe established the framework within which all subsequent complexity would emerge. What makes this story remarkable is not merely that such dramatic events occurred, but that we can reconstruct them. Through careful observation, mathematical reasoning, and experimental testing, humanity has traced the universe's history back to nearly time zero. We've pushed understanding to energy scales exceeding anything in our everyday experience by factors beyond imagination. Mysteries remain. The Planck epoch's details elude us. Inflation's mechanism isn't fully known. Dark matter's identity awaits discovery. Questions about why existence occurs at all lie beyond current science. Yet the broad strokes stand firm. The first second's major events, the phase transitions, the cooling, the particle creation and annihilation, rest on solid theoretical and observational foundations. Consider the journey light has made to reach us. The cosmic microwave background photons we observe today last scattered off electrons when the universe was 380,000 years old. Before that, they bounced between particles through the opaque plasma. Earlier still, they existed as part of the radiation bath during nucleosynthesis and the Hadron epoch. Earlier yet, they were created and annihilated countless times during the quark epoch and earlier phases. These photons carry information from throughout cosmic history, encoded in subtle ways we've learned to read. Or consider an atom in your body. The hydrogen, a single proton nucleus, formed during the first second when quarks bound together as the quark-gluon plasma hadronized. That proton has existed for 13.8 billion years, surviving in various environments before eventually becoming part of your body. The carbon, nitrogen, and oxygen atoms formed later in stellar interiors and supernova explosions, but their existence depended on the universe having protons and neutrons to fuse together, which depended on the first second's physics proceeding as it did. The first second represents a boundary between physics we understand well and physics at the frontier of knowledge. After 1 second, conditions fall within ranges explored experimentally or described confidently by established theory. Before 1 second, we push toward energy scales and densities where current theories strain or fail entirely. The Planck epoch remains largely speculative. Yet even here, theoretical frameworks provide guidance, making testable predictions that future observations might confirm or refute. This story will continue evolving as observations improve and theories develop. Perhaps we'll detect primordial gravitational waves, confirming inflation and revealing its energy scale. Perhaps we'll discover dark matter particles, illuminating early universe physics. Perhaps new particle accelerators will probe higher energies, testing grand unified theories directly. Perhaps quantum gravity theory will mature sufficiently to make definite predictions about the Planck epoch. Each discovery will refine our understanding, adding detail to the picture sketched here. Some aspects might change dramatically if unexpected observations contradict current models. Science remains open to revision when evidence demands it. Yet the overall framework, hot Big Bang, expansion, cooling, phase transitions, seems robust. Too many independent observations confirm these broad features for them to be fundamentally wrong. As you rest, consider that the atoms comprising your body, the air you breathe, the planet beneath you, all trace their origin to the first second, the forces holding atoms together, the properties making chemistry possible, the light illuminating our world, all established during that opening instant. We live within the echo of creation, inhabitants of a universe whose fundamental nature was set before the first second finished ticking away. The universe that emerged from that first second has given rise to stars and galaxies, planets and life, consciousness and civilization. From quantum fluctuations during inflation to human thoughts pondering their origin, spans an almost inconceivable gulf in scale and complexity. Yet physics connects these extremes through unbroken chains of cause and effect. The same equations describing quarks and gluons also describe, in principle, every atom and molecule, every biological process, every thought and perception. This unity underlying nature's apparent diversity represents one of physics' deepest insights. Whether examining the universe's first second, or the workings of a living cell, the same fundamental principles apply. Energy conserves. Symmetries constrain possibilities. Quantum mechanics governs small scales. Relativity governs fast motion and strong gravity. These principles, established during the first second, persist throughout all subsequent evolution. Sleep well knowing that the universe's story, though beginning with unimaginable violence and energy, has led to a cosmos rich with structure, beauty, and meaning. From the chaos of the Big Bang emerged the order we observe, galaxies and stars, life and consciousness. The first second set the stage. The billions of years following filled that stage with performances more intricate and varied than anyone could have predicted from initial conditions alone. Tomorrow continues the story that began in the first second. The universe expands, stars burn, planets orbit, life persists. The physical laws established during that opening instant remain in force, governing everything from nuclear reactions in stellar cores to neural signals in brains. We participate in an ongoing cosmic narrative whose opening chapter was written before the first second elapsed, but whose later chapters remain unwritten, shaped by choices and chances yet to unfold.